Thank you for the introduction, and it's my great pleasure to be here to give a talk, and also especially to finish this random planar map day. So my plan for the talk is I will first give a detailed explanation of the so-called hamburger cheeseburger bijection proposed by Scott, which is also advertised in Jason's talk. And after that, I will present my joint work with Yuan Green and Cheng Mao, who are also my friends from MIT. So I should apologize if you don't have any idea what's going on here. That's because I make a last-minute change to decide to use the blackboard to make a slide. So you can treat it as the next slide after this. Sorry. So okay. So suppose we have a planar map M with a edge configuration on M. So here the map is this graph with 10 edges embedded in the plane, and the edge configuration is colored to be blue. So we call these edges the open edges. And then you can have this classical loop representation of this pair. So what you do is you first connect all these dual edges of the closed edge, and so I color this dual edge by red, and then for every face. So for every face, you connect this dual vertex to these vertex on the face, and in this picture, I color these edges by green. So in this way, you if you count this blue edge, red edge, and the green edge, you will get a triangulation with two n faces if the map originally have n edges. And if you only count these green edges, you get a quadrangulation with n faces. And the quadrangulation has two types of quadrangles. So one type is containing the edge, and the other type contains the dual edge. And then you can you can draw loops passing all these middle points of the green edges, following this pattern. Right. So now you have a collection of loops. And these collection of loops, it encodes the information of this pair. This is very classical in FK model. So now I want to assign some weight to this pair. The way you do it is you let the joint distribution of M and E proportional to square root of Q to the number of loops. So Q is a number between 0 and infinity. And if you do this, you can see that condition M, the conditional distribution of E is a critical FK cluster model on top of M. And if you consider the marginal law of M, it is given by the partition function of the critical FK cluster model. And this particular random object is called the critical FK random planar map. Okay, so in my talk, I will only focus on the case where Q is between 0 and 4, because as already mentioned in Jason's talk, in this range, this FK cluster on top of random planar map has close relation to CLE kappa on top of a Lever quantum surface. So the relation of the parameter is Q equals to 2 plus, and then so kappa is between 4 and 8, and gamma equals to 4 over square root of kappa. Okay, so I'm only going to focus on this range. So a very a very useful tool to study this random parameter map is also using bijection, but instead of using the pretty well-known CVS bijection or BDG bijection, so we use the so-called hamburger-cheeseburger bijection. So the hamburger-cheeseburger bijection, in short, it gives the bijection between this pair to a word of burgers and others, which I will explain later. So I will first restrict my attention to the case where E is a spanning tree. Okay, so let's see. Okay, so now you have a same random, you have the same planar map, but the edge configuration is actually a spanning tree. And then you draw this red edge. These 4 red edges, they give you a dual tree. So you have a pair of spanning trees. And you can play the same game as here. And since you have a pair of trees, you will only have one loop. And this loop is something like a discrete piano curve. So and this loop is actually traverse every triangle once, and then it naturally gives a sequence of triangles. And then you can match triangles which are in the same quadrangulation, which are in the same quadrangle. For example, if you draw the sequence here and you match these quadrangles, you can see that it's a Kastelyn pattern. So, and the reason is very simple. It is because if you only restrict your attention to a tree or a dual tree, it is actually just the contour exploration of the tree. And so what you can also do is you can replace these pairs of triangles into these pairs of directions. You can replace these pairs of triangle into up and down. You can replace this pair by right and left. And then you get a sequence of 4 directions. And this is just another way of saying it is a walk on Z2. And this, if you want to transfer this Kastelyn pattern into the language of walk, it's actually saying that this walk is in the first quadrant. And moreover, it returns to 0 at time. So this is a walk of 2n steps and satisfy these 2 conditions. Okay, so till now, this canonical bijection between a pair of map decorated with a spanning tree to this walk in the first quadrant returning to 0. This map is this map goes back to Moulin. And the reason why Moulin introduced this bijection is to enumerate how many pairs are there in this set. And you can imagine that it is possible to enumerate such kind of walks. And so now I want to introduce another sequence, and this is the idea of Scott. So so I replace this up-down direction by what I call the hamburger and the hamburger order, and this right and left direction by what I call cheeseburger and the cheeseburger order. So you can imagine you are in a particular type of burger restaurant. There are 2 types of burgers, hamburger and cheeseburger, and there are 2 types of customers who will order hamburger and and the other will order cheeseburger. And then you can replace this sequence into such a sequence of, so this sequence has 20 letters of these 4 symbols. And then, so how to translate this constraint in terms of burgers? So what you can do is you can imagine you have a burger stack and a order stack. both of them are empty initially. And then you can read this word from left to right. So whenever you read a burger, you will add it on top of the burger stack. And whenever you read the order, you will eat the topmost corresponding type of burger. For example, here we are keep adding burgers on top of the burger stack until we find this. Sorry, I think I misread the orders. For example, so if I meet an order here, what I will do is I will eat the topmost hamburger, and if I read a cheeseburger order here, I will eat the topmost cheeseburger. And this way is actually another formulation of this Kastelyn pattern. So why we are interested in this burger restaurant? So till now there is no benefit of introducing such a burger restaurant, but in the general case it will be very helpful. So now this slide makes sense. Okay, now we consider the general case. So in general case, I'm not able to draw an actual planar map. So I'm only going to draw this bunch of loops, because otherwise there will be too many edges, and then you have to double the number of edges to draw the to give the burger sequence. So imagine you have a FK cluster, and this is the loop representation. Okay, so now I want to give a procedure of decreasing the number of loops until the number of loops is only one. And then after I have only a single loop, it is actually a map with a spanning tree. And then I can apply this Moodian bijection. So the way you do it is, suppose this is the root. This is the root and the dual root. So there must be a loop. So you start the exploration from here. There must be a loop. So we call this loop the L0. So this L0, it is not the only loop in the whole configuration, and this means that this L0, it must pass certain numbers of pivotal quadrangles. By pivotal, I mean if you flip the edges inside that quadrangle, it will change the number of clusters. So, and then what you do is you find the last. You find the last pivotal quad. For example, in this case, maybe you have pivotal. Maybe you have the pivotal edge here, and you have a pivotal edge here. You have a pivotal edge here. You have a pivotal edge here. Okay. So then, so this is the last pivotal edge if you explore under this loop, and you'll find this pivotal quad, and then you flip this quad. So if the quad looks like this, you flip to this, and if you look like this, you flip to this. And this operation will only decrease the number of clusters. For example, here, if you flip, what it will do is it will give you and then you absorb such a loop. So in this way, you are enlarging your rooted loop, and then you can return to the first step until you find a single loop, and then you got you are in the situation of Moodians. So basically, and actually, this procedure can be reversed. The only information you need to track is these marked quadrangles. So basically, we can conclude that if you have a general configuration, and then it is corresponding to it is corresponding to a walk on the first quadrant, returning to 0 plus some marked steps, some particular marked steps. And these marked steps, they corresponding to these flipped pivotal edge. So and now what's the meaning of this in terms of burgers? There is a very easy way to encode this information marked steps by introducing another types of customer. So this type of customer, it will only order fresh order. So by fresh order, I mean if you so you keep read the word of these 5 symbols, and if you meet a fresh order, what you do is you just eat the topmost burger, regardless of the type, because he only prefer the freshest. So then what you get is a word of line 2n with symbols in these 5 letters. So the way you do it is, so if you want to get a if you want to get a word from a pair of M and E, what you do is you first do this procedure to get M and T, and after you get M and T, you get such a sequence, and then you find all these marked pair of burger and orders, and then you flip the corresponding order into this fresh order. And the way it will work is because the particular rule you choose quadrangles. So basically, so it also satisfies the rule of, so the burger stack is empty and the order stack is empty. So now if you have a word which contains these 5 symbols of length 2n, and it satisfies the condition that the burger stack and order stack are both empty at the end of the day, then what you can do is you can first find the match of all these fresh orders, and then you flip the type of fresh order into the right type. For example, if a fresh order eats a cheeseburger, then you flip this fresh order into a cheeseburger order, and so the hamburger case is similar. And then in this way you can identify all these marked quad, and after you identify all these quad, you can flip back to get these loops. Okay. So now this burger restaurant become making sense. So this is a nice deterministic bijection, and how can I use this bijection to sample this critical FK cluster model? So the way is actually very simple. So you just have a IID sequence of random variables, and each takes value in these 5 letters. So you have IID sequence of random variable in these 5 letters, and you assign such weight. So basically, this means there is a p fraction of your customer who wants to eat a fresh burger. So, and then let's denote this word by W. So you just need to sample the word in this way, and then you condition on the fact, condition on the event that this burger stack and other stack are both empty. And then you apply this hamburger cheeseburger bijection to get a pair of M and E. This way you get the exact sampling of critical FK cluster. Why this is true? If you think about how we define these fresh orders, you will realize that whenever you add a fresh order, you are decreasing the number of loops by 1, because the fresh order are just corresponding to this marked quad. So so the number of fresh orders is exactly the number of loops minus 1. So and on the other hand, if you sample if you sample a word W using this weight, the weight of W is actually proportional to 2p divided by the number of f's. Even after you condition on the fact that both the burger stack and the other stack are empty. Okay, now you just need to set the square root q equals to 2p divided by 1 minus p. And then if you choose this p according to this equation, you get exactly the sampling of critical FK random parameter map with n edges. So here, since q is between 0 and 4, this p is between 0 and 1/2. So this is the finite volume case of the FK model. And you can also consider the infinite volume version of this, which is you can take a local limit. The way you take the local limit is, so here we have a rooted map. And now, so according to this Schramm-Benjamini topology, what you want to do is you want to find a finite ball and then take the n to infinity to see what happens in this finite ball. But we can also reroute this edge. So we can uniformly pick an edge according among these edges. This won't change anything. So you repick an edge, maybe an edge here, and then you pick the ball surrounding this edge and see what happens locally. And on the side of burgers, for example, you have this sequence of burgers. What you have to do is you only need to uniformly pick a location and see what happens around this location. So it is proved in Scott's paper that so if you sample the word W according to this IAD sequence, then the probability that both the burger and outer stack are empty, it's actually have a sub-exponential decay. And this means, and on the other hand, by Cramer theorem, the portion of these different letters, they deviate by these typical portions. That probability will going to have exponential decay. So this conditioning will not matter after you take this local limit. So at the end, what you get is so if you want to consider the infinite volume version, if you want to consider infinite volume version of this FK, what you will get is a bi-infinite sequence of letters. And these are just IID sequence according to that weight. And then it is also proved in Scott's paper using some basic ergodic argument saying that so every letter in this bi-infinite sequence, it almost surely has a match. In particular, every fresh order in this sequence, you can almost surely find its match, which means you can apply this hamburger cheeseburger bijection to this infinite volume, to this bi-infinite sequence. And then what you get is a double-sided random walk with a weird measure. Okay. So this is basically the discrete picture behind this mating tree paper Jason just talked about this morning. So everything in the continuum actually works very nicely. So I'm not going to be able to explain anything in the continuum, but I'll give you this table. So this FK loops, they correspond to CLE kappa, this kappa between 4 and 8. And the planar map, it corresponding to a linear quantum gravity surface with parameter gamma. And this exploration path, it corresponding to the so-called space-fitting SLD, kappa. And then it is proved in the Scott's paper that this two-sided random walk you get from the hamburger-cheeseburger bijection, it will actually converge to a two-dimensional Brownian motion. And but this two-dimensional Brownian motion also have a parameter p, which code the covariance matrix. So yeah, so I'm not able to review the continuum stuff because there's a huge amount of literature to establish all of this. For example, this the definition of the CLE kappa is given in the CLE paper 09, and this linear quantum gravity is defined in the famous KBZ paper 08. So the construction of the space-fitting SLD and its relation to the CLE kappa is given in the imaginary geometry 4, and and to get this Brownian motion from the space-fitting SLD on top of the linear quantum surface, it is actually done in the mating tree paper. And also, I want to comment that in the mating tree paper, they also only deal with the infinite volume case. And in the infinite volume case, this linear quantum gravity surface is actually a quantum cone. And so, okay. So the motivation of our work is actually to improve the convergence. Because this convergence only tells you that the exploration path, it converges in the topology of these pairs of walks, but but it doesn't give you too much information about these loops. So we want to prove some convergence result for the loop observables. So we already seen from here that the number of fresh orders equals to the number of loops minus 1. So it suggests that the number of the loop information should have close relation to these fresh orders. And actually, these FK loops you can read off using what I call F excursion. I'll explain this later. And in the continuum, the CLE loops, they can actually be read off by the so-called pi/2 cone of a Brownian motion. Okay, so what I mean by F excursion. So let's look at this picture. Sorry. So let's look at this picture. So in this picture, so this is a route and this is a dual route. So if you travel along the loop, this quad is the marked quad you want to find, and then you want to flip this quad to get a actual exploration path. And in this picture, this quadrangle is actually corresponding to this one. So this picture here, it actually corresponding to this sequence, but you replace this C by F. So the image of this pair under the Hamburger-Chiesler bijection is given by this sequence. Okay, so so now it's natural to say that. So let's suppose this is the target point that I want to look at. Oh, sorry, maybe I want to look at this one. So suppose this quadrangle is the target point I want to look at, and then so this loop is surrounding this quadrangle, and in particular it will surrounding it with a cycle, with a blue cycle. So and what this exploration path do if you flip this edge is exactly given here. So you flip this edge, and this exploration path goes to here, and then it will enter this cycle, and then it will travel everything. It will visit every triangle in the cycle, and then it will go back, go out, and then finish the whole loop. So basically, it means that if you want to count the number of triangles inside this cycle, you only need to find how many steps does the loop goes inside this cycle. And so the starting point of this loop is this one, and the end point of the loop is this one. So these two steps, they exactly corresponding to the C and F. So so what I call the by F excursion is just for any F you find a match, and then for the whole word in between, I call this segment of word F excursion. So you can imagine that this F excursion is actually encode the information inside these cycles. At least the length of the F excursion, it tells you how many triangles are there inside this cycle, and this can be a discrete notion of area. And if you want to count how many edges on the boundary of the cycle, what you only have to do is you only have to find you only need to find how many orders in between this F excursion which are matched outside this F excursion, because by definition these boundaries, so the definition of the boundary are like it is so the quadrangle contain the edge only visit once by this loop. If it is visited by twice, then it is like the interior by this of this loop. Okay, so you can actually extract the area information and length information of this cycle, and in the random walk picture, this segment from here to here, it actually corresponding to this part. So this is a cheeseburger, this is a fresh order. So actually corresponding to this, and by the definition of a fresh order, you can realize that from here to here, it will always contain in this quadrant. Otherwise, it will contradict the definition of the fresh order. And then you can imagine that if everything works nicely, if you take the scaling limit, then this guy, it will converge to something like this. So this is the Brownian motion. I want to remark that so this can only happen for Brownian motion which has positive correlation, and this is actually the case for the p between zero and 1/2. So if you have a independent Brownian motion, I think there is I think the probability that you get such a figure is 0. Okay, but actually one needs to be a little bit careful about what is the meaning of area of the loop or length of the loop. So actually the cycle here that I'm talking about. In the continuum picture, it corresponding to so it doesn't corresponding to the area of the whole loop. For example, so a typical CLE loop look like this. This is a CLE loop. It will touch itself and this way, and then suppose this is a target point. So the cycle I'm talking about just now actually corresponding to this bubble here. But you can imagine that if you are more careful, you can represent the other information about the loop using the language of F expressions. Okay, and our main theorem is basically saying that so all these microscopic So our theorem is basically saying that all these microscopic F expressions, if you draw the corresponding random walk path, it actually converges to the parallel to cone of Brownian motion. And in particular, all these area and the length of these loops in the discrete, they converge to the corresponding quantum area and quantum length in the continuum of the CLE. So the reason why I want to say it's a microscopic excursion, because if you want to do a scaling limit, it doesn't make sense to consider these small loops, these small F excursions. Okay, so the main technical ingredient in this proof is the following. So let's consider. So I define a quantity called J. So the definition is I condition on x0 is equal to F. So I condition on that at 0 you got a F order, and you want to find the matching. It is a COH. And J will be the length of this segment. This is a random variable. So we show that this J is actually regular varying with exponent So we show that J is regular varying with exponent kappa over 8, and if you have familiar with Levy process and stable laws, you can see that this is also equivalent to saying that J is in the attractable domain of stable law. So the real definition is given by saying that the probability J is bigger than n equals to n minus mu times Ln. And this Ln is a slow varying function. So this is a key technical ingredient we proved. So in Scott's paper, he actually proved that the expectation of J is infinite, but he didn't consider the more fine tail behavior of this random variable. So why this is assume we have this. So I want to outline the proof of this of my statement. So actually, our result is a very general statement about F excursion converging to cone time. It's a little bit abstract, but I want to give a typical example of this theorem. So let's So suppose this is minus n. So this is in the discrete case. This is minus n and this is 0. So we consider the maximum f excursion, which the location of f is smaller than 0. And it includes this minus n. So we consider such a macroscopic f excursion. The reason I choose minus n is because this is actually the scale of time. And then we show that the location of this f, it actually converges to the, so after rescaling, if you scale by n minus 1, it converges to the maximum pi over 2 cone of the corresponding Brownian motion. So this is a pi over 2 cone time, and this pi over 2 cone it will cross the time moment minus 1. So this is one of the corollary of our main theorem. To prove this, so it is convenient to read the by infinite word backward. So you read the word from 0 to minus infinity. And then sorry. So you read this word from 0 to minus infinity. And your job is to find the maximum f excursion crossing minus n. So what you will do is you read the word. Whenever you find f, you find its match. So if this match is already cross minus n, you find the maximum f excursion. If it is not, you can keep reading the word until you find the next f. And you keep read, and well, finally, after some steps, you are going to find this maximum f excursion smaller than 0, containing minus n. And if you think a little bit, you will realize that this is actually a renewable process. And this is a renewable process, and this time segment. So this is the time you find this f. This time segment is actually a very classical quantity in renewable theory, which is called residual life or something. And there is another very classical theorem by Dynkin and Lamperty. The theorem basically says, so this segment has a scaling limit if and only if this increment has a regular varying tail. So this result is similar to something like if you want your random variable to be in the attractable domain of a stable process, this random variable has to have a regular varying tail. They're in the same flavor. Okay, so after you know that this guy has a scaling limit, this position of f has a scaling limit, and also if you look at this continuum situation, then there is a similar renewable structure, and inside this pi over 2 cone time, and so you actually going to have a regenerative set. And this point is actually the last point in this regenerative set before minus 1, if you're reading backward. And so there's also an analog of Dynkin-Lamperty theorem in the continuum case. So you just need to compare this formula. It is a so-called generalized arc-sine law. Okay, so I still have some time to talk about a little bit more details. So to prove such a kind of statement, we initially want to use some combinatorial argument to do some enumeration, but we didn't manage to do that. Instead, we are looking at so we are trying to prove this. So you can see that if you prove this, it's actually equivalent to this. The way you prove this is it's basically saying that if you condition on this f excursion to be big, to be bigger than n, then the probability that it's bigger than Cn is kind of decays like a power law. Sorry, C is bigger than 1. And what we actually prove is we prove that if you condition on j is bigger than n, this f excursion is actually converged. It converged to a Brownian motion condition on state positive, condition on state in the first quadrant until time 1. So this condition is like saying that the backward random walk condition on stay in the first quadrant until time 1. And what we prove is actually this guy has a scaling limit, which is the right limit. And so the probability that the Brownian motion stay in the first quadrant until time 1 is a 0 probability event, but you can define by taking a limit. And this is actually defined in a paper by Shimura in 85. And we also use some very sharp estimate in Shimura's paper. And I also want to comment that this random walk in random walk inside a cone is was a pretty active topic back to early 80s and late 80s and early 90s. Okay, so we actually prove this, and then we can get the desired result by taking an expectation. So this is basically the main content of the talk. And I want to mention 2 related works. So one related work is by, sorry, I have to find the name of the author. So one of the related work is what I learned just last week. So the work is given by Nathaniel Nadia and Ray. So they also consider a similar problem, which is the critical FA cluster model, and also using this hamburger cheeseburger bijection. But their perspective is a little bit different from ours. So they basically focus on computing the tail exponent of the length and area, and they also got this value here, but it didn't got this slow variant correction. So and the other nice feature of that work is you can find a very detailed explanation of how to encode the information about loop using F excursions. Another work is by David Wilson. And myself. So that work concerns abelian Sand pile on top of the random parameter map. So, but since the abelian Sand pile also has close relation to uniform spanning tree and unicycles, you can actually also use hamburger cheeseburger bijection to study that. We actually evaluate the Sand pile density on top of that, and as a byproduct, we also compute the joint law of the cycle area and the cycle length of the unicycle. And all of these three works, these two works and our work, they will appear on the archive soon. And so I also want to mention a ongoing work. So the ongoing work is about it's about study the finite volume case of the FK cluster model. So so far we are only considering the infinite volume version, and this is easy to handle because you have an IAD sequence of random variables. But also very interesting question is to just consider the original setup, which you have 2n letters, and you condition on these letters to be empty, which means you really consider a random walk in the first quadrant, and also returning to 0 at the end point. And another question is to show Scott's convergence result. So that is interesting in its own, and also that will give you some property of the limiting object. So the limiting object should be something like a Brownian motion condition state in the first quadrant until a certain time, and it will return to 0 at the end point. So this will be a joint work of Yuan Guin and myself. Okay, I will finish the talk by returning to the open problem which Jason already mentioned this morning. The open problem is to understand the diameter of the FK cluster map. So so basically, if you follow this hamburger-cheeseburger bijection, so from here to here, you get from a general cluster of configuration, you will get a configuration of a map with tree, but the map's structure doesn't change, which means the metric structure of the map is actually just a function of the walk in on the first quadrant. So so it must be a deterministic function of this walk. So if you can really extract any information of this metric using the walk, it will be very nice. Maybe there is some way to get upper bound or lower bound. And if you can understand the discrete case, usually there is some corresponding analog in the continuum. And we already know that in the continuum case, based on Duplantier, Jason and Scott's work, we know that this pair of Brownian motion it actually determines the whole thing. And maybe you can also read off this Brownian map from this pair of Brownian motion. But although I have no idea how to do it, but this is certainly an interesting question. Okay, thank you.
Thank you.
Okay.
So you are saying that in the discrete case you are expecting that walk to be a Brownian motion?
Sorry?
You're saying that you're expecting it or proving that it's a Brownian motion?
Yeah, we are working to prove that this is actually a Brownian excursion inside the first quadrant.
And how, what is Q? What does it do to this? Because the law of this depends on Q.
Yeah, so we have the relation between, so we have this relation, so for any Q, you have a unique P, which is the fraction of the fresh orders. And also I remarked that the Brownian motion obtained in the mating tree paper is actually also depends on this P. The coordinate structure depends on this parameter P. So for any particular value Q, you have a certain positive correlated Brownian motion.
I have a question regarding this correlated thing, because one thing one wants to do is to say that it's actually just the image of a Brownian motion in a cone by the map that maps it.
Yeah, but the angle of the cone can be different. So if you have different coordinate structure, then it means that So basically, if you map this correlated Brownian motion into independent Brownian motion, then this parallel to cone, if you map into a cone, into a Brownian motion inside a wedge with some other angles. And this angle is another parameter corresponding to Q.
Yeah. So, but this is, you never use this.
This appears in this.
Yeah. So you will look. This is
Exponent.
used behind the scene there.
Yeah. So this kappa is also depends on Q. There's only one parameter.
Sure. This was the way.
So clarify again, you actually do prove?
No, we didn't prove. We are working to prove.
That's what you're working to prove.
It's in progress. Yeah.
Other questions or comments? Okay, let's thank the speaker.
Thank you.